All right. Hi, everyone. Can you hear me clearly? All right, great. My name is Yousif Hussin. I'm a security engineer at Google. The way I got into security was very long ago when I was very young, a little kid. I somehow developed some passion for breaking stuff in general. I kind of had some disappointing experiences when somebody would give me a computer and I'd be like, can you help fix this? Because you seem to like computer stuff. And I'm like, sure. And take like half an hour or an hour, and I come back and be like, here you go. And then they say, OK, thank you. It's not coming on. And I'm like, I know. And they said, but I thought you fixed it. I was like, no, I didn't. But here's a cooler thing. I managed to break it. So they got disappointed. I'm not exactly sure why, because I thought that was a pretty cool thing, especially if you can break it remotely, right? So the next time I'd be like, hey, my sister would come. The first time was my brother, right? This time it's my sister. She's like, can you help fix this? And I come again. But this time it took me a little longer. I tried to be a little bit more innovative this time. So I came back and I was like, yes. It's all good. And then she said, but it's not working. And I said, well, yeah, but I found a way to break it. So even if you take it to someone else, they wouldn't even fix it. And I did that remotely over the wire. Like I wasn't even on the machine. So I mean, it's pretty awesome, isn't it? So that somehow I kind of took that into a career. So yeah, and there are, of course, a lot of other cooler things that I really used to like to do. And somehow I think when you start developing this kind of passion, there are like two tracks. You can make money, or you could get in trouble. I think I was lucky I decided to go with the good way. So I've worked in the security industry since 2007, roughly. That's how I started. I was in the US at a company called TiVo. I don't know, for those of you in the US, you probably know of it. That one? Yeah, it used to be cool back in the days. Now I'm not sure. I worked at Apple, Meta, and Microsoft before Google. And in the past, like maybe 8 years, I've focused more on like, hey, we got hacked. What do we do now? Kind of work. It was a lot of fun for like maybe the first 6 years. But then I got a little bit stressed out. I was like, OK, this is a little too much. Now I joined Google. And right now, I'm in a team called ISE Systems. And what I do is vulnerability research. So basically, it's kind of like the story I was telling you about my family. Like, I'm literally giving a system, be like, find a way to break this. And I just find enjoyment in doing this. Trying to threat model it, understand the intricacies of it. How does it work now? How can I make it behave in a way that is different, nobody knew about? And then I will go to the developer and be like, hey, this is probably not a good idea. Let's fix it this way. When I joined Google first, I was in a team called the Vulnerability Coordination Center. The Vulnerability Coordination Center is a team that's really interesting. What they do is they do incident response for vulnerability remediation. And they focus on the supercritical, high-scale, complicated vulnerabilities that affect Google products. So when I was at that team, I wasn't doing vulnerability research. I was doing remediation of something that's already been found. And the talk I'm actually presenting today is going to be more relevant to that role. At the same time, I've been part of the team that does the bug bounty program for Google. So I do the on-call, receive the reports, research, and then reproduce the exploitation and see if that's a vulnerability. And then we give them money if it's a good report. And at the time, I was actually in both teams. I was the only one that actually straddled both teams at the same time. So there were some times I would be like on this side, the bug hunter side, and I would triage something, and then I find out, whoa, this is so big. It's so big, it needs to go to the Vulnerability Coordination Center team. And then I would escalate it, and then I would go on the other side, and I'd be like, OK, now I'm going to pick it up here, and I'm going to do the remediation for this big thing. And now I'm in ISE Systems. ISE is short for Information Security Engineering. And it is the team that is responsible for securing Google products in general. So Vulnerability Coordination Center, how does the team do that work? First of all, there are like a couple of things the team does. The first one is they monitor the public domain for news. and then they say, that sounds like a vulnerability that could be interesting for us. Let's try to find out if this affects Google in any way. And then they would write a report on it. And sometimes, if it doesn't affect Google, we'll just close it. If it affects Google, we then find a way to fix it. So that work was manual. And so basically, it looks like this. Get the intelligence from the public domain, look into Google. Is it affecting Google? Is there a fix or no fix? Now, I wanted to automate that process. So that was kind of like one of my first projects at Google was like, OK, well, the public domain does expose a lot of APIs through which you can get all this kind of information that we're just looking online on with a browser, right? So how about just get that information and then ingest it in an automation platform that we can build ourselves. And then Google internally, pretty much anything talks APIs, and you can basically just get whatever information you need. So we could basically just turn this into an automated platform. Get the intelligence, look into Google, decide if it needs a fix or not. Now, the other role, this is the one when we got a big vulnerability and we want to fix this. How do we do this? And I'm going to go through the details of this. I can tell you about how it works, but I think it's probably better to just maybe kind of do it together, just go through the process. So, but before we do that, we're going to have to go back to like university. I'm very sorry. But I'm sure some of you are excited about this, and some of you probably aren't as excited, but I need to build a little bit of context. Oh, yeah, thank you. Thank you. I was waiting for someone. Thank you. We're going to have to go back to build a little bit of context around some of the fundamentals just to make sure that we're all on the same page so that you can follow easily with the rest of the presentation. But also, there are going to be some questions I'm going to ask later. So if you pay attention here, you might be able to answer them later. I don't have Google swag, but I'll say good job. First of all, a question. Can anybody look at this and tell me what this is? 0, 1? Very good answer. Excellent answer, actually, because if you try to make sense of this and you can make sense of it, not only am I impressed, but I'd really love to be your friend for a minute, or something, if that's possible. There's no way. It's a very unrealistic expectation for somebody to look at bits and make sense of it, right? So, but as we know, computer works with zeros and ones, right? That's how they operate. Now, if you want to talk to a computer and you want to tell it to do something, you have to give it an instruction, encode it in bits, one way or another. Now, as you know, in computers, we've got the CPU that takes a set of instructions, and under the hood, there are registers, like little boxes with memories in them, and then the computer would move things around these registers, right? So if I want to tell the computer to do something, and I cannot talk in bits, how do I do it? So the first time, I know that the easy way is to write a C program, and it will be compiled and end up. But you don't always have to do that, right? Let's say we want to go down one level, right? So the first time I was kind of introduced to this challenge of looking at bits and trying to interpret them like a computer, somebody told me, you don't have to do that. How about we step back and basically modify that set of bits into what you're looking at here, right? This isn't an instruction, right? It's represented in something called the assembly language. I'm sure most of you know of it, or if not all of you. Then the first time I saw this, I was like, wow, that did not help. What does that even mean, right? OK. So I was earlier I was saying that the CPU would move things around between registers. So this is a very simple instruction that basically tells the computer to move something from a register to the other. It's very weird, actually. It's like move, yeah, you can work that out. But it doesn't actually move it from register 1 to 2. It's actually the other way around. It's like move from EBX to EAX. And these two are basically the register names, right? So it looks like this. Move from EBX to EAX. That's an instruction to move bits from this register to this register. Very simple. But then there is this instruction, which is a little bit more complicated because it doesn't actually have operands. It doesn't tell you to move where from where or to where. I mean, the thing that makes this a little bit more interesting is that the machine already has a set of instructions that will perform behind the scenes if you give it this one. So it already implicitly knows the source and the destination. And then if you look at what comes before it, rep is basically short for repeat, like do it again. So this is an instruction, and this is basically the setup I was telling you about that the CPU performs to be able to tell to move from where to where. But you don't have to worry about the details here. Something that is important is this rep. If you repeat an instruction and you put rep twice, and you tell the computer to process this, would this break the machine? Would this cause a problem? Can anybody tell me? Yes? No? Maybe. Will it repeat like double the times? Actually, it turns out that it just ignores it. It's not a big deal. Yeah, it'll just be like this. And then if you give it another like couple, yeah, the same thing. Yeah, it'll work just fine. But this is a very important property. Now, something slightly different. There is a feature called ERMS. It's an optimization feature in the CPU to make the CPUs more efficient. You make them more efficient, you can build them more cheaply, right? So that's kind of the goal. It's short for, if I remember correctly, because these names are just so bad, ERMS, Enhance, Repeat, Move, Store. I have to review them every time before this, whenever I do a talk about these things. So it's an optimization feature just to enhance the efficiency of the CPU. There is a problem with that feature, ERMS. If you're moving data between two registers and they're under 128 bytes, the overhead that goes around the optimization overweights the benefit, so it really kind of doesn't make sense. But if it's more than 128 bytes, then yes, you're actually effectively become more efficient. But this is what gets addressed by the other feature called FSRM, which is short for Fast Short Repeat Move. And with this feature, you do the same optimization, but it doesn't matter how many bytes you're basically moving. So this feature is in Intel CPUs. So the last thing that I want to mention is, in 32-bit machines, we had 16 like standard registers, right? 8 registers. 8 registers. But then we've got like the 64-bit world where we've got like these 16 registers. But the problem is that when you look at the operand, the name of the register, EAX, EBX, these are like 3 bits. So they can address how many registers? 8, right? So what do we do with that? How do we address that problem? So instead of like fixing the entire paradigm of like, hey, let's make this bigger, the operands, they thought we could basically just do a little bit of a hack, right? Remember that prefix that I talked about that gets ignored? That actually has like a size in it you can use. So if you look at this, EBX is 3 bits, and you can basically use it to address 8 registers. Now we've got 16 registers, and we've got the prefix. What they do is they would basically borrow a bit, so now we've got 4, and that basically gives you 16. And that way you can address 16 registers. This is something to keep in mind. The last thing I'm going to go through back in university is this. Does anybody know what this logo represents? If you know? OK, nobody knows. Great. So we're going to get back to this later. It's interesting. So now I'm going to go through a response story. So when I joined Google, after all the rejections that I've had from Google, you know when I talked about Meta, Microsoft, and all these companies, I've always wanted to join Google, but I always got rejected. There is this one time I managed to get in. I hacked my way through legally and joined, and I was super excited. So I was like, I want to work on a really interesting project now. And then they gave me a task to perform, and it was what I'm going to talk about here. Fuzzing. So now, a lot of times, when you break into a CPU or find a vulnerability in a CPU, or actually any computer system for that matter, or application, you can basically just look at wherever it takes input, throw a lot of stuff that don't make any sense, and then you see how it behaves to all of the different permutations of the input that you give to it, right? And then once it behaves in a slightly different way, then you'd be like, stop. Why is it doing this? Because that could be a pretty good indication that the system has a bug. That could be a security-related bug. So a security researcher at Google does a lot of fuzzing on CPUs. And one of them was basically doing fuzzing for Intel CPUs, one of the research objectives. So they figured out that when they were doing fuzzing on Intel CPUs, there are certain conditions when they apply, and you give it certain input. And if you use the prefix that I just told you about earlier, and that feature, FSRM, the optimization feature, is enabled, that would basically lead to this. What I mean by this is a system crash. Like it's an MCE, machine check exception. And that basically led to a vulnerability called Reptar. So that was kind of like the start of the project that I worked on. Like, OK, well, they found this. So now, Yousif, you're in the Vulnerability Coordination Center. This seems like a problem. Can you deal with this? So I was like, OK, what do we do? How would we even start? I mean, I'm super excited for the aspect of exploiting it. But fixing it is maybe fun, but maybe not as fun as the exploitation. But anyway, the way it works is that at Google, actually, this standard is pretty much adopted globally generally, is that a vulnerability is identified, and then you would set something called an embargo period. It's like 3 months where nobody talks about this, and we have to fix this vulnerability. And then by the end of this embargo period, we should publish this to the public domain. So we had to go through this process, and we work with the vendor on this. And we also collaborate with other similar companies, like, for example, Amazon, Microsoft. So we establish this embargo period, and then there is this process that we have to go through from the start until the end. I couldn't help it. I'm just a Nintendo fan. But anyway, you get the point. So it's like a few months. And I'm going to go through the process from the start to the end. So first of all, to actually go through this process, there is something I want to mention quickly. There is a set of protocols that we follow at Google for responding to incidents. And when we respond to incidents at Google, it doesn't even have to be a hacking incident. Like if it's a vulnerability that was identified, we already assume that's an incident, and then we deal with it. So if you just give me a second, I'm just going to do something quick. OK. Actually, we're here. All right. So I'm going to get back to the incident response process later. The first thing that we do following the IMAC protocols is something called an impact assessment. An impact assessment is basically like understanding the vulnerability and then, OK, how bad is it? How can it be exploited? How easy can it be exploited? And how bad is it in terms of like the impact radius? What machines does it affect? Things like that. Now, if we think about this, we started from this, right? We started from like the single machine. You run the exploit, and it will crash. But then it doesn't really sound like a big deal, does it? Like, OK, you've got the machine. You run the code, and it crashes. So it doesn't sound like a big deal. By the way, just to introduce this person is a security engineer that I heard about. He's called Leo. You might see him chiming in a couple of times. I heard he's a very bad security engineer. We'll see about that. But he's saying it's not a big deal. If you agree with him that something like this is not a big deal because you're just crashing your own machine with this, can you just raise your hand? OK, thank you. So there is an interesting concept that I like to introduce sometimes with like food. You know when people say sharing is caring? I don't always agree with that statement. Like, you could actually get in trouble just by sharing, and especially when you're talking about the computer world. Like, imagine if I know that you always have a meal with someone, and I have access to that someone's kitchen. I could basically affect you just by the nature of being able to go to that kitchen and put something in the food, right? So when we're talking about computer worlds, we've got like also this concept of sharing, right? Especially today, right? Everything is pretty much shared. So if you crash a machine and cause an MCE, the lower level, part of the machine, then that becomes a problem, isn't it? Because then you're basically shutting down everybody else's virtual computer, right? If you have a hypervisor. So what? OK, now that we understand this, can anybody tell me like a name of a product that might be affected by something like this at all? Oh, OK, excellent. Google. Yeah, exactly. That's actually a very good answer. You kind of like read our mind because that's actually the next slide. So you've got Google Cloud. It's like, imagine at scale, you basically just go and run this exploit like in Google Cloud, like horizontally, and basically just shutting machines all across. And it could be pretty bad, right? It could be pretty bad. So that was our #1 product because it is pretty much big. It's an important product, probably one of it's one of our most important products, but also the scale of it. And the threat model applies to it directly. So the way it works is that an attacker could just spin up a VM in Google Cloud, and all you have to do is basically just run the exploit, and now we end up shutting the machines adjacent to you in the same physical infrastructure. Not very complicated. So now, I mentioned earlier this logo. So this is something that we use at Google called, before I say what it's called, back in like 2003, we were like thinking, OK, well, we really got to use our machines a little bit more efficiently. We can't just give every team a virtual machine, dedicated machine, just do their work, whether that's physical or virtual. So we have to really kind of share the resources a little bit better. And that's when we introduced like the concept of basically breaking down the machine into different logical parts and then sharing that effectively across teams and actually across all of Google's data centers for everything that we run. And that is called Borg. And then later on, like, I don't know, 20 years later or something, that's become something in public domain that we use today. Can anybody tell me what that is? The equivalent of it that we use? Yeah, Kubernetes, right? So that's how actually Kubernetes was born. Initially, it was a project at Google called Borg. And today, we still use Borg for pretty much everything at Google. So it's because of the concept of sharing internally at Google also, this is affected by this vulnerability. So that was the other part of the vulnerability impact assessment is that, OK, well, it's not just Google Cloud, but actually pretty much all of Google, because we've got all of these servers internally running Borg. And surprisingly, Google Cloud actually also uses Borg under the hood. So it was affected by this. And yes, Borg is basically used across Google to manage all of our software deployments in all of our data centers globally. But is that all? Like, can anybody tell me where else? Not only Google, but generally, somebody might be affected by this. A very important segment. It's very important. Well, we've been talking about servers, but we don't care about clients? Yeah, sorry, I'm looking at you because you've always answered. Yeah, but I'm not going to pick on someone. Oh, somebody did? Oh, I'm sorry about that. I actually didn't notice. Is it you? Go ahead. Where? Client. Yeah, exactly. Yeah, client. But here's a question for you. You're shutting down a client machine. Why is that a problem? I mean, client machines shut down all the time. Just the convenience, right? I mean, when you update Windows, it just slaps you across the face and be like, restart, right? Like, it's never been a big problem. Right? Why is it a problem? OK. We'll get back to this. I wasn't actually expecting like an answer right away, but it's fine. So when it comes to Google specifically, we've got Chrome OS. Chrome OS is our client devices. By the way, if somebody raises their hand and I don't actually talk to you, feel free to come up and just fight me or whatever. Yeah. Anyway. Of course, I was talking earlier about the Windows update, right? So you get something like this. It's fine. It's an inconvenience, shutting down the machine. So this guy, again, is just saying, this is not a big deal. Maybe it makes sense. I don't know. But we'll get back to this. Here is an interesting aspect of this vulnerability response process. Because when we reported it to Intel Intel knows a lot about the inner workings of their CPUs, right? A lot more than us. We were doing a black box testing. We were just fuzzing it. When we reported this vulnerability to them, they looked into it a little bit more in depth, and they found out that, well, initially it looked like this for us, but then it looks like this for Intel because they can see all of the internals of it, and they could privilege escalate, basically. So it could lead to privilege escalation, the same vulnerability. So nice, right? It's very cute when you get privilege escalation, because now the topic of client exploitation comes very relevant, right? Now, is it easy to actually exploit a client device through a browsing session? Like, can you open a website with some code in it, somebody would browse in it, and somehow you exploit it with a vulnerability like this and shut it down, and privilege escalate and also the machine? It's very difficult. In theory, it's possible. It's very difficult to do, but in theory, it's possible. So we had to assume that it's possible. So what do we do next? We were like, OK, server machines, client machines. But how many client machines and how many server machines are affected by this? And we basically just get the numbers, right? We just go to like whoever owns that kind of product, and they'll be like, OK, can you give us access to the system with which we can basically query it and ask you the question? OK, how many do we have? I know some of you, or a lot of you love SQL, so we had to do a lot of this kind of stuff, like, OK, let's get the number of the machines for all of these products, basically just documenting them down as part of the impact assessment document. But now that we know, OK, well, this is the impact radius, this is where we're affected. Now, the next question that came along was, how do we fix it? We know it's bad, it's big. How do we fix this thing? And there are like a couple of ways to fix it, right? Basically, one way is we could wait for the vendor. I don't know about your experiences with vendors when they fix stuff, but they are not always 100%. And the other solution is basically you can come up with something innovative yourself. You could fix it yourself. But that's not always easy, right? Generally, the expectation is that the vendor will fix it. But then one of our engineers, this young lady over here, she came up with an idea. She was like, how about this? This could fix it. Can anybody tell me what this is or what she's thinking about? No? It's fine. Chicken, right? I'm just being a little bit silly here and giving you like the logo of a chicken and some stuff that don't make any sense. This time, the name they came up with is actually pretty innovative, better than FSRM, ESR. Are you ready for it? It's called the chicken bit. But anyway, so there is a bit that comes with a feature in a CPU you can flip. It's kind of like on-off. It's called the chicken bit. And basically turning on off the feature that they introduced to you. Remember earlier I was talking about FSRM as a feature that is required as part of this exploitation to work when they did the fuzzing? So she was like, just disable it. Now the exploitation wouldn't work. So that's a solution. It's effective. It works. But feel free to raise your hand and tell me why this would be a problem. I had the answer earlier. Huh? You always answer again, and then you it's fine. Yes, but you're correct. So initially, it was an optimization feature. So imagine you go to Google Cloud and be like, turn off this feature. From a security perspective, it's perfect. But from making money, I'm not so sure. So basically, they tested it. So they did turn off the chicken bit as part of the testing process. And they found out that the performance goes down by like 10%. So this is big, right? It's very big. But in my opinion, when I was working on this and I was leading the response, I was like, that's not a bad thing. Because we're still in the process of trying to fix this. What if it gets leaked? Maybe we're going to get to a situation where it's better to go down 10% than 100%, right? Like, what if somebody just finds this vulnerability and they want to target Google and be like, let's just go and shut down everything, right? So we might come to a decision. We're like, well, just keep it in our back pocket. We might come to a decision and be like, let's use this one and go down 10%. It's not too bad. But at least it's not the worst situation. So we kept it in our back pocket. But then later on, the good news is that actually the vendor did provision a fix. So we were fine with this. They provided something called a microcode update, which you basically just do a BIOS update in your machine, and it will apply the fix to your CPU, and it will get fixed. But here is another problem. Google Cloud or Borg. OK, we understand the optimization aspect of it, but what about restarting the machines? Is that a problem? So I'll get to this in a little bit. So we've got these solutions, right? Server platforms, we've got and the clients, actually. It's pretty much the same solution. We've got like the chicken bit and the microcode update. There's a high performance impact if we do the chicken bit. Now we're going to talk a little bit more about the microcode rollout strategy. So there is something called PV testing, which is production validation testing. We make sure that it actually works very well in an individual machine. And not only us, but also other companies like Amazon or Microsoft, they would also do this, and they would all say, good. So this small circle of organization would test together and be like, OK, we'll find this to be effective. So we did this. But now, how are we going to roll it out? OK, well, we can do the BIOS update and restart all the machines and be like, OK, well, there's no other thing we can do. And then tell the customers, we're sorry. We're going to have to do this because we're fixing a very important vulnerability. But what about if we do it in memory? Because when you load the machine, you got everything that you work with in memory. What about if we just fix it there? Let's not go down and actually apply a fix to the firmware or anything like that. How about we just go to the running memory and be like, fix it, so it's live, so we don't restart it at all? And that actually is hot loading the microcode into the CPU. And it is something that you can actually do. It's not very popular in the public domain. I think it's kind of being frowned upon, like, oh, it's dangerous. But it is something that you could basically do. So it's called hot loading the microcode update. So if you look at memory and how it works in general, so you've got the machine that's turned off. You turn it on. You've got whatever it is that you're running from the firmware up to the memory, and then everything is fine. Now, if you got vulnerable code, and you fix it in the situation of the BIOS update, then you turn off the machine, turn it on, then it gets fixed in memory, and everything is fine. But we've got the problem of the hit of the restart. But what about if we do this? Just fix it in memory, right? Very smart, very clever. But it's something that we really need to test properly because it hasn't been popularized in the public domain very much. So we thought, how about we just test it ourselves, like at scale, and see how it goes? And that's basically what happened. So we tested this with a good number of machines at Google. And we were like, I think we're confident enough we can actually roll this out. Just hot load everything, which basically means we fix it in memory. We don't restart anything. And the next BIOS update cycle will get this hard-coded, right? That's kind of like the idea behind it. And we rolled it out to all of Google Cloud with zero effect. Now, is it really 100% transparent? I mean, in terms of application performance, there's no performance issues at all. But if you look at the CPU cycles itself, if you really, I don't know, unless you're like a cockroach or something, you just go all the way down. Yes, the cycles are actually going to alternate a little bit differently. So there is a bit of a difference. But as far as impact on the application performance, there's nothing. Now, when it comes to the client, the situation is a little bit easier. Because in the client situation, all you have is really just sending the updates to the client. And the client themselves can also download the fix to themselves. Now, this is kind of like a big part of the process that we had to go through. And now I'm just going to give you a bit of a glimpse into how we did manage this in terms of communication and team structure at Google. So incident management at Google, like I said earlier, is like a process that we follow with protocols on how to respond to incidents. But one of the very important aspects of it is that you have this hierarchy of team that is responsible for this. And when I joined Google, they gave us a training on this. And they tell you this is the only time you can boss your own boss, because you're basically responsible for this entire process, and you're ultimately responsible, and you can lead everybody in it. And your boss might be part of the response. So, but also, it's not like the only cool thing that you boss your own boss, because you're responsible for this. If things go down, you're kind of in trouble. So, how does a team look like? Well, of course, imagine if this is a team. Like, that's me, like the best team ever, right? It would be very, very nice if you could just, push the buttons everywhere yourself and just take care of everything. But unfortunately, that's not really how it works in the real world. Let's start with something called the operations lead. Somebody that's responsible for all of the operations of the response. And generally, that would tend to be somebody who's super technical and is very familiar intimately with all of Google's infrastructure. And then reporting to him would be like a data center response lead, somebody responsible for all of the infrastructure in data centers. And then under that, there is like the person that's responsible for cloud. And of course, these are all leads. And reporting to these leads are big teams. So the team is actually much bigger. But I'm only showing the leads. Just to give you a bit of an idea of the scale of this response, of course, we've got also for Chrome OS a response lead, corporate systems response lead for like internal systems. And then we've got like tech research lead. This is somebody that is leading the tech research, like, hey, the people that discovered it, did they have any other relevant findings in regards to this, and fixing it, and things like that, or testing systems to identify if the system is vulnerable or not, things like that. Vendor engagement and tech lead. This is like a tech lead that is responsible for talking to Intel. Communications lead. If we communicate anything internally or out externally, this person is responsible for formulating how we do that properly. And of course, that includes like somebody who's leading internal and somebody leading external, technical support for Google Cloud, GCP, and then we've got a legal lead. Why do we need all of these people? Like a legal lead for also approving things like external communications and things like that. So there's a bit of a legal aspect to it. And then, of course, there's like the lead for non-Google alphabets. Does anybody know what that means? Non-Google alphabets? Yes, that's correct. Repeat what? Oh, you mean the answer? Oh, OK. Yeah, I was actually going to do it. So basically, it's non-Google alphabet companies. So a lot of people kind of tend to get confused a little bit, like thinking Alphabet is Google. It's not. So it is an important part, but it's not the only one. So we've got, like, for example, Waymo and a bunch of other things. Like some of them, like Chronicle and other companies that used to be an Alphabet company, became part of Google later on. So that's an important element because the NDA that we signed as a Google company with Intel was Google Intel, not Alphabet Intel. So we couldn't actually fix the rest of Alphabet before everybody in the public domain got the information and fixed it also. So the rest of Alphabet was treated like any other company. So we get to this point where we have to do something called disclosure, which is like, OK, how are we going to communicate this to the public domain? We have to tell them, OK, this is a vulnerability, this is the impact of it, and this is the fix if you want to fix it in a way. Or when it comes to Google Cloud, we don't actually have to do anything because it's already fixed internally. So we're just telling you, hey, good news, there was a vulnerability, and it's fixed. You don't have to do anything, kind of thing. So we do this in the form of something called the security bulletin. I'm sure a lot of you are familiar with this. So we publish this on our Google Cloud and other places in public domain. And then people know about this vulnerability. And if you look it up, like if you Google Reptar, you'll find some information about this. And now we've got it disclosed, and we're happy, and we're done. And I can basically say, well, that was one of my first projects. It was my first big response that I had to lead at Google. I was super excited. Now I can basically go on holiday, and I'm happy with this, right? Now, here's something important I want to mention. The research team that I mentioned earlier, they developed a tool called the Icebreak tool. Icebreak tool is a tool that you run in any infrastructure, and it will tell you if you're vulnerable to Reptar. So it's a very valuable, interesting tool, right? Because not everybody is just using Google Cloud, right? It could be anything. It could be like on-prem physical devices that you have, and they run Intel CPUs. So we publish this tool. So now that we know this tool, there is part of Google Cloud that's called Cloud Shell. It's like an interactive system. You can basically go on your Google Cloud environment, and you can run commands on your environment. It's very easy and nice to use. So after all of this, and after we're done, and the story's finished, pretty much, or maybe not yet, we've got somebody from the public domain sending us this message. Just heard about Reptar. I tried running the Icebreak tool on Cloud Shell on Google Cloud, and it worked. So I don't know if that's dramatic enough. So what does that mean? Like, the fix didn't work? Google Cloud, OK. By the way, all of these people that were screaming here and panicking, I'm not even one of them here, right? This is the team, right? I think I was on my holiday, like I said earlier, going to Hawaii or something. I can't remember. I think it was Hawaii. While during my flight, I was just checking on my laptop, and I saw this message. And I was like, I think I had a parachute with me, but at that point, I was like, you know what? Let's take off. So no, it wasn't that bad. But the thing is, we were a little bit concerned. I was like, what the hell is going on? We really need to get on this. Just when I thought it was over, well, maybe I was wrong. So we did investigate this immediately. We got some people to look into the Icebreak tool, run it in the system, and see why it's showing like things are vulnerable, or why did the fix not work. We have to do this immediately. We have to do something about this immediately. So turns out that there was somebody discovered that the Icebreak tool had a bug. So he was giving you like a false positive, like, hey, you're vulnerable, but you're not. And we were like, nice. I'm so glad I didn't actually make that jump. Yeah, and then we fixed that bug, and now people can use the tool correctly without any issues. So that was kind of like the response. So there are some of the questions that we had to ask after that. Like, what did we learn from it? What can we do better? 2 minutes. What can we do better? Can we automate? Are we prepared for the next one? So one of the things that I feel like I did a really good job at, not just trying to sing my praises here, but following that protocol of IMAG was very important. I'm sure you can relate to this when you're dealing with like hacking incidents, when you're like in the forensics team. You don't want to just make decisions in panic. So having this kind of process that we follow on a team and a structured set of people that can lead this work was super important. It was actually more important than I thought it was going to be, because then we focused only on the analytical human aspect of it, and then we don't actually have to panic. That was very important. Can we automate? Yes. We do have a very impressive set of tools at Google that we can use to automate a lot of this work. But I wouldn't say it's perfect. We should leverage some of it and build on top of it. Are we prepared for the next one? I do believe that Google is very well prepared, given the experiences that we've had, especially this one. So one of the things I worked on at the end of this response is a project called the Google CPU Response Toolkit Automation. This toolkit is basically an automation that I created that will bootstrap the response, and it will automate a lot of it so that the people can actually only focus on the things that need human intervention. So that will basically set things like the response artifacts, documentation, team structure, how we're going to roll out the fix, things like that. And then we only focus on the things that cannot be automated. That was kind of like an output of the response, and I worked on that project myself. So this was the flow of the response end to end. And it's actually, I think it was pretty cool that it ended up with a lot of learnings, but also producing this automation that I created as a result of it as well. I hope this kind of helped you with some of the insights that we shared at Google. By the way, that's my email. I think it's pretty easy. Feel free to reach out. I'm also on LinkedIn. There are a lot of really smart people here that would really love to make new friends on LinkedIn and stay in touch. And so I can learn from other people as well. Thank you so much for attending this.
Big round of applause, please, for Yousif. Unfortunately, because the schedule is really tight, we don't really have time for questions. Although I'd love to know if I could turn that into a hypervisor escape from workload to workload. Anyway, later. That's something for later.
Yeah, just want to not to interrupt you. Just want to say one thing. Actually, I would prefer if you have questions for me, like during the breaks or anything like that, we could have a chat. I'm more than happy to do that. Yeah,
Yousif will be in the coffee area. If you've got any questions, grab him there. We're going to crack right on now with our next presentation. Large round of applause, please, to Yousif again.